trains like this. And this sort of a trend and similar trains have been used in many scientific inferences. So here, your straight line model does not work. So then what you do here, straight line in the sense that it's linear with respect to your auxiliary variable x. But then you can probably fit it using a sum of polynomials. Okay, so this is basically a set of basis functions, and these are the coefficients, and this is basically the function itself. And you can see that you are able to fit this data very well. Now we'll touch upon this particular issue, like, is it worthwhile to fit your model, to make your model fit every data point? Because all of these points may not be reliable. They may be part of the noise in the data, and we'll talk about those later on. But the main message here is that, you know, when it may be in a situation where simple y equal to ax may not fit your data, in which case you have to use some polynomial. But the coefficients like a, these are actually your model parameters. And it can still be linear in model parameters, but it's non-linear in x. Okay. But there's another kind of learning, which is perception. And that's kind of hard to explain just using what I talked to you about right now. And I mean, using some kind of a model fitting. Say, for example, you are looking at some numbers. It's a number 9. It's a handwritten number. And we all can recognize that this is actually number 9, even though it's quite different from the actual number 9. Similarly, you can have a number 8. Because, you know, people have different kinds of handwriting, so they can't really reproduce the numbers the way they're typeset, and you have different forms. So this is another number 8, and, you know, I mean, depending on the context, human brain can recognize what these numbers are, even though the number is even though this is blurry, very noisy. Sometimes we can basically say that this is number 9, but just without any context, you can't say exactly what this number is. So this is something that human brain can sort of, you know, recognize quite easily. So how does our brain work? The way it works is that it looks at a whole bunch of different possibilities of writing different numbers, and then it learns in a way that is basically statistical. So brain is nothing but a statistical decision organ. And you will see later that we will actually devise a machine learning algorithm that can also recognize different handwritten digits only after we have trained it with lots of known answers, handwritten digits, and give it the actual answer and let it learn the pattern. And then if you bring in a new handwritten digit, it should be able to recognize that. Okay. And of course, you know, none of these are completely guaranteed to work, and there may be situations where they may fail, and there can be multiple possibilities, and that happens with us also. Okay. Another thing that is kind of difficult to explain in terms of equations sometimes is color perception. So here we have different colors, and so the reason I'm talking about all of these things is that as scientists and engineers, we have to deal with different kinds of data sets. They come in different shapes and form. They can be digital data, they can be analog data, they can be some handwritten notes, but all of these have to be taken into account before you can make an inference. So that's why we really have to look into all of these different kind of data sets that we come across. You can get color pictures of, say, surface geology, and does that really tell us something? In fact, it does. Geologists friends would tell you that, you know, some rocks have certain characteristic colors. And so the problem of inference becomes hard when there is high dimensionality. By that, what I mean is that you just don't have one factor, but many factors. to use to take into account because before you can make an inference. When you have complex irregularities, this could be nonlinear, could be non-stationary. Now, the most difficult part is when you have little prior knowledge, okay? And that's when we run into a whole bunch of difficulties. And also we have huge data sets that we have to fly through and identify some of these things. Now, in this context, I'd like to mention that recently people have been looking into incorporating physics into some of these machine learning algorithms. In fact, that is one of the primary areas of my own research, and my students are working on that. So we can sometimes bring in our prior knowledge in terms of the physics of the problem, and basically build in some of the equations from physics, assuming that even physics is not always correct. So we can allow for some variations in the physical models. So having said that, so what is machine learning in that case? So machine learning, so we start with a simple example. And just to demonstrate like where machine learning has become very, very useful. So this is a Netflix challenge. You all know what Netflix is, right? You watch movies on Netflix. So Netflix, if you watch a movie, next time you turn on Netflix, it will basically come up with a whole bunch of suggestions, similar to the ones that you have watched before, right? And that's kind of a smart thing to do. And that's also very useful because then you don't have to basically search through some 100,000 movies to be able to pick ones that you like. So this challenge is just to predict how a viewer will rate a movie, right? When you choose a movie, it comes up with something called, I think it's called IMDb rating or something like that. And so how a viewer will rate a movie is very important because that's what is used in making suggestions to you as to what movies you want to watch. And if you can improve on the prediction of rating a movie, just a 10% improvement can basically fetch the company $1 million, because then their membership goes up because members are happy with the way members are happy because they get to watch movies that are highly rated. Okay. So the sense of machine learning, then, so how does Netflix do it? It uses machine learning. So basically, the assumption is that there is a pattern that exists. We cannot pin it down mathematically, but we have data on it. So we look at a whole bunch of data sets, and based on that, we can look at some patterns. So nowadays, when you go to grocery stores and you buy things, I don't know if you go to say some good grocery stores, then they even ask you for your phone number. And what they do is they associate your phone number with the kinds of things you are purchasing. And so they basically come up with this pattern of your need. So what kind of items you like to buy. So next time they have something similar to this, they can send you a text message or they can send you an ad. So that way they can attract more customers. Now, there are many different ways people have defined machine learning. Arthur Samuel said it's the field of study that gives the computers ability to learn without being explicitly programmed. And I'll explain it to you a little bit later, because if you just read this sentence, it really does not quite make sense. I think I like Kevin Murphy's definition. It says these are algorithms that automatically detect patterns in data and use the uncovered patterns to predict future data or other outcomes of interest. So when there's a lot of data sets, say for example, Netflix viewer data or even grocery shopping data, the millions of people are actually shopping and millions of people are viewing Netflix. So all of that data set, there are some patterns that you cannot view manually. And then this algorithm can go through all of these data sets, and then it can directly detect some patterns in the data. Okay. And there's a definition by Tom Mitchell, and he basically says that you perform some task and improve your performance with some experience. Now, this is more like how machine learning does it than what machine learning is. But I would say that I like Kevin Murphy's definition the best. So the comparison, in the first lecture, I told you about the way we solve our forward problem or solve our inverse problems, right? We bring in some data and we have a program that basically iteratively models my data, changing the model parameter and feed these to the computer. And the output is a model, okay? But in general, in machine learning, especially in the supervised learning, which I'll explain to you in a bit, you input the data and your expected output, or rather your output that you already know. And then you present a whole bunch of these to the computer. And this basically outputs a trained network to which you then put another unknown data set, and then it can predict your desired output. So here, this is your traditional programming. You have data and program, feed it to computer, and it's an output. And this is mostly physics-based, but it doesn't have to be. Or it could be empirical also to start with. But then machine learning uses data and an output which is known, gives those to the computer. Then there's an output, it calls it a program. And this program is now fed in here. Okay, so in other words, you have actually modeled a mapping from data to output. Okay, so you can say that my data and my output, I can relate these two by simply developing some function operating on the output to give me the data. Okay. So where does machine learning fit in terms of discipline? It's highly cross-disciplinary, and that is one of the reasons you are seeing students from different departments. But to be able to understand machine learning, you have to use some tools from applied math, optimization, linear algebra, particularly convex optimization. You need to bring in ideas of statistics. In fact, I'll give a lecture each on optimization and statistics. And of course, from some ideas from computer science for algorithm design, data structures. And this is a very interesting field. If anybody is interested in learning that, that would be really nice, like how you make machine learning algorithms faster. So that's where computer science comes in. And also psychology and physiology, because biology of learning is basically what was modeled to start with, and some of the new algorithms are looking into different concepts and different models built in psychology and physiology to actually further develop some of the more advanced neural networks. So if I were to basically explain to you how much each one of these discipline influences our learning of machine learning, linear algebra, probability theory and statistics, multivariate calculus, algorithms and complexity, and others like biology. I'm sure most of you actually have had courses in linear algebra, probability, and calculus. If you don't remember, you can just go ahead and review those. But I will also and also ask me so that I can give you some background while I'm lecturing. So just don't feel shy. Feel free to interrupt me whenever you feel like. Okay, so history of machine learning. So machine learning is not all that new. What is new is actually deep learning, and that has revolutionized the whole industry or academia. Neural networks were proposed back in 1960, and then in 1985, they proposed multi-layer perceptions and restricted Boltzmann machine. And then support vector machines were invented in 1995. In fact, that's when I also got involved in using some of these applications, and came up with some new algorithms for looking at geophysical data sets. And then we have deep belief network, a recurrent neural network, convolutional neural network, and max pooling. So I will talk about all of these things. And convolutional neural network and deep learning is what actually made the difference. And that's what made it possible for machine learning to be so popular with application to numerous problems. So, artificial intelligence is the discipline where you try to emulate human intelligence. It's a general discipline under which you have machine learning, and then deep learning is another advancement in machine learning algorithms. Okay, so today actually AI is ubiquitous. Like whatever you do, you see that AI is being used. For example, when you do a search in Google, and it basically comes up with all possible related subjects. And there is some AI algorithm working behind it. And on smartphones, you can actually see you have these. Also, you have Siri and Alexa, where you can actually dictate something that you'd want to do, and the machine recognizes that and actually does the work. And then there's a lot of work going on autonomous vehicles, and you can actually see even in Austin, Texas, sometimes Google and Tesla cars are driving. Of course, they've had some accidents, but autonomous vehicle or autopilot is a hot field. So as I said, it was invented back in 1960, but then why has it suddenly become so popular in the 2000 or so, in the year 2000 onwards? Well, this is because not only there are better algorithms, we also have more compute power. Nowadays, if you have GPUs, these can really, really fly. Big problems can be done very, very quickly using sophisticated computer hardware, and also has a lot of memory. Not only that, we have been able to collect a lot of data sets. We have the storage, increase in storage much more than what we could store earlier. And we have better algorithms and models, and this is improving. All of these things are actually improving. Okay? We started off with simple PC, then went to workstations, then went to parallel computers, and now we have GPUs. So this figure actually shows you that with the increase in the amount of training data, we have been able to predict more and more accurately some of these scenarios. The thing that you should remember is that the hard problems for people are easy for AI, and easy problems are hard for AI. You will recognize that. And AI can do a particular task, and maybe two tasks, very, very efficiently, very, very quickly, better than human beings. But human beings can do a lot of different things. So that's why, I would say that AI has narrow intelligence, but humans have general intelligence. Okay. And the machine learning approach, it can be useful when there is a difficulty of hard-coded approach, like the examples I showed you, like in handwritten digits and things like that. But then it looks at some patterns. So to recognize those patterns, it has to identify certain features in the data. Okay, so it has to first determine what features are to be used. So by that, what I mean is that let's say that you're trying to look at some objects and let the machine identify whether it's, say, a cat or a dog let's say a car. So each one of these has certain features. For example, a car has a wheel, then it has headlights and things like that. So these are some of the features that the machine should be able to detect before they should be able to use before it can say whether it's a car or an animal or some fruits and things like that. So feature determination is very, very important. And in fact, for feature estimation, one of the ways you can do that is using unsupervised learning, which we'll also talk about. And once you identify the features, then you have to learn to map the features to the output. Okay. Say for in this data set, you have two different kinds of data sets. Okay, and we'll give you a lot of examples of those. And there is a line that separates these two. Okay, and you can see that there can be multiple possibilities. This is called logistic regression, and we will definitely discuss that in great detail. It doesn't have to be linear separator. This could also be some kind of quadratic separator like ellipses, okay, or parabola. So ML approach, first you collect some data, they're called samples. Then you select a model, and then we estimate certain parameters that can relate your input to the output. That's very important. You have an input and you have an output, and you want to relate your input to your output. Okay, using some machine learning model, and in between it has to pick some features from the input to decide how to use those features in your machine learning model. And then once it's been trained, then how does it predict the unknown output? And that is a part of what is called generalization. Okay, and once it's been generalized, then you can use it for your inferences. So there are different types of machine learning. Based on the type of data, you can have supervised, unsupervised, or semi-supervised machine learning algorithm. Then there is a method called reinforced learning. And also you can classify machine learning algorithms based on the type of output. It could be regression or it could be classification. Then also based on the type of model, it could be generative model or it could be discriminative model. And let me tell you a little bit about each one of these methods. So what is supervised learning? Supervised learning is one where you actually give a known output to the model. Say for example, these are some fruits, and you can say that these red figures, each one of these is an apple. So you tell your computer tell your algorithm that these are apples, and then feed it to the model. And then what happens is that when you bring in a new apple, then it recognizes that this is an apple. So this is supervised when you actually train the algorithm with known answer that this is an apple. What if you didn't tell the algorithm that this is an apple, but still help the algorithm to learn? And this is called, that method would be called unsupervised learning. Say for example, I have apple and bananas. Okay. Now unsupervised algorithm would look at these different patterns or different shapes. Say for example, apples are more like rounded shape. On the other hand, bananas are elongated, and also it can recognize color. So apples, let's say that is red, and banana is yellowish. And based on that, it can distinguish between these two classes, and it can basically tell you what is apple and what is banana. We're not going to talk about apple and banana in this case, but this is just an example. And you can think about many things which are very, very many things that are kind of analogous. For example, you have different rock types. Okay, so can the computer recognize those rock types? So there are some minerals in a rock. If you take a slice of a rock and then look at it under microscope, and then can it recognize different grains of the minerals and things like that. A supervised learning is mostly used method. Say, for example, spam classification of emails. So once you get an email, you can see that sometimes those emails get sent to your spam folder, okay? And how does your algorithm know that a particular machine learning, particular email is spam? Well, it can look at certain characters, a certain pattern, and certain words. Typically, when it finds a message that says that you have won a lottery worth $1 million, immediately that gets sent into your spam folder. And of course, there are ways people are even beating that by hiding it. But bottom line is that there are certain characteristics, certain features in an email that are used to classify emails from spam or non-spam. Similarly, face recognition. Again, face recognition is actually working quite good, but it's still also not 100% correct. And of course, people have started to think in terms of medical diagnosis systems, and this is more of a hype right now because, again, the same problem. Even the doctors oftentimes really don't know all the details of the diagnosis, and it develops while treating a patient. So I don't think this is at a stage where you can use it in an automated manner like the face recognition or spam classification. Okay, so there are some examples. A supervised classification problem is offshore oil transfer pipeline. So here, input data with dual energy gamma densitometry here. And in this, say for example, you have 6 beam and there are 12 measurements. So you look at the attenuation of the gamma ray density, and based on that, you can try to calculate certain properties and use those to infer the fraction of oil, fraction of water. Okay, so in the subsurface, you're not able to see what's hidden in there inside the rock without breaking it. So can we actually send something like some kind of some of our representative, for example? So we're sending gamma densitometry in this particular case. And there are other methods. You can send acoustic waves, but then they don't tell you directly as to whether the rock has any oil or water. So there are certain features in your scattered data that can be used to identify the occurrence of oil and water. So this is one example where we do supervised classification because we have trained our algorithm with a lot of known answers. Okay, so we take some samples where we know there's oil and there's water, and then we collect a lot of data sets and use that data set to train it. Then when you go to the field and do this experiment, you can automatically detect whether there's what fraction of oil you have or what fraction of water you have. Okay, so, oops, I think I'm going backward. Yes. All right, so now we look at another way of classifying machine learning algorithm. Classification. So let's say that we have data sets x1, y1, x2, y2, and x and y sub n. So here, this is a data set for medical diagnosis. So here we have plotted the tumor size, and based on that, we can decide whether the tumor is benign or malignant. So if you look at this, so you can basically code your data in essentially in binary format. If it's 0, this is your benign, depending on certain size of the tumor. That's equal to 1 if it's malignant. Again, don't ask me if this is 100% correct, because even the medical doctors are sometimes, mistaken about diagnosis. But let's say that this is the kind of data that is being used for diagnosis. The main purpose of showing this is that this is a different kind of data set where the variables are either 0 or 1, as opposed to the linear fitting or nonlinear fitting that I showed you earlier, where x is a function of y, and y could take any value between, say, 0 to whatever. In this case, they are 0 and 1. And this could be, you can also represent it as 1 or 2 or plus 1 minus 1, doesn't matter. Bottom line is that there are two discrete values, okay? So given some data set, when you are asked to decide whether it belongs to one class or the other, this type of machine learning would be called classification. Again, this can be done in a supervised way. Now, regression is the method where we're actually using data that, say, for example, is real valued. I just already mentioned this to you. This is very different from the data set that I showed you earlier in the classification. Classification data are like 0 and 1 or plus 1 or minus 1. But in this case, it can take any real valued function where you can fit a line or you can fit a polynomial, and you can use that for prediction. What if you took this data set that I showed you earlier and tried to fit a line, least-squares line? What would that look like? That would likely look like this, right? But that's not good for prediction. So you have to use special algorithms that can be used for classification. Okay, so here, a little bit thing about learning does not necessarily mean fitting the data. So here, I've shown you two different data sets. In the data set, you have two different classes, for example. And how do you distinguish between the two classes? So here, you can separate these two very, very nicely using a line, which is basically a combination of different straight lines. It actually classifies the given data set perfectly. On the other hand, you can use this line to also separate these two data sets. So the question is, which one is better and why? Of course, in terms of data fitting, if you look at the error, this is a lot less compared to the one to my right. But then some of these data points may be noisy. So fitting every data point is not necessarily a useful thing to do for prediction. So we use some notion, it's called simplicity. I don't know how many of you are familiar with something called Occam's razor. Of all possible solutions, use the one that is simplest, okay? And then, of course, the question is, what is complexity? So these are some of the things we deal with when we actually define our optimization problems and different kinds of norms that we will talk about next week. So the main point is that any algorithm that you design must have the ability to generalize. Means that it should be able to, they need to perform well, not just on the training data, but on new inputs as well. In fact, I don't know how many of you participated in this hackathon that I had organized a couple of months ago. And we gave some data sets which the students were asked to train. And then there were a particular data set that was actually not used in training. And we used your model to predict that. And based on that, we decided who was the winner. So the main idea is to be able to generalize, okay? And there are different, many functions and variables that we have to worry about in designing those algorithms. That's what machine learning theory is all about, which we will definitely discuss. Okay, so unsupervised learning is without labels. So when we provide some data set that has known answers, the known answers are called labels. So get used to these terms. Label data means the data set with known answers. Okay. When we don't have any label, then we actually use unsupervised learning. So for example, here we have these different data sets, and we want to do a classification. Well, you can actually see that these different points cluster in different regions. So you can use algorithms called clustering, which we will discuss in great detail. And you can see that using clustering, we can group these to different clusters. And you can see right away, like how can be one easy way of thinking about clustering is to say that, okay, I can pick some locations in this two-dimensional space, and I can pick all points that are closest to the center of that particular point, and then I can say that these are my different clusters. Okay, so there are different ways of clustering. Especially the one that I talked about is one of those, and there are many more that we'll talk about. Yeah, so we have many different ways of doing unsupervised learning, so clustering. We can also use something called PCA, or principal component analysis. Again, that is something we will discuss. Then, of course, autoencoder is a deep learning algorithm where we do that. And you will see a lot of applications of this in every field. And in geosciences, particularly, we're using these now on a routine basis for classification of rock types like lithology, fluid prediction, and so on and so forth. Okay. There is also another algorithm that is called semi-supervised. So what it means is that you train a model with part of the level data set, and then use that to predict the unlabeled data, for which actually, well, first of all, you can use a part of the labeled data also for prediction, and then use that for predicting unlabeled data. So there are many different semi-supervised algorithms. And one of the things that we have devised is actually we run the training. So we have data, and then we run it through some network, and then it has an output. Okay, but we don't know what the output should look like. So then what we can do is, what I do is I run it through my physics and then predict some data, and then try to match data against data. So this does not require any label, but you can think of this either, you can call this either unsupervised, but even though this is unsupervised, this does not fall into the category of classification. And you can also call it semi-supervised, because we are actually taking this output and then running through the physics, assuming that I know the physics of the problem. So that's where you can call it semi-supervised. Okay. Okay, so there are places where semi-supervised can be successful. It basically helps you speed up your process. Now, there's one method that I'm not going to discuss in the class because this is, there are too many topics to cover. So reinforced learning. Reinforced learning is a process where, let's say that you have an input, which is an apple, and your response is it's a mango. But then you give it a feedback. It is no, it's wrong. It's an apple. And this is noted because this is used as a penalty. However, if you did find this to be an apple, then you get a reward. So there is this penalty and reward as a part of training that is used in reinforced learning. And in some applications, this can be very, very useful, but I'm not going to talk about that in this course. So you have some notes. Okay, so quick example of regression. A regression problem would be, what is the temperature going to be tomorrow? So given certain certain temperature variation today. You want to predict what the temperature tomorrow is going to look like. So this is basically a continuous variable, and it can take any number. So this is in Fahrenheit, 84 degrees Fahrenheit, and so on. Well, you can turn the problem around and you can say, well, all I want to know is that, is it going to be cold or hot tomorrow? But then when you say it's going to be cold or it's going to be hot, you have to have some marker that basically can classify them into two categories like cold and hot. So for example, if the temperature is below 60 degrees, then I can say that it's cold. And if it's above 60 degrees, this is hot. So now this is a classification problem. This is like a 0 and 1 binary decision, okay? So I was just giving you this example. So this is an example of this tumor size. And you can see that if you try to fit it with a straight line using regression, then this fails miserably, right? But it's a perfect fit. It's a bad model. And of course, the regression problem I already told you. I'm not sure if you're able to read this. I should probably type it properly. So there is this method called generative and discriminative. A generative model are probabilistic model of each class. So basically it finds the boundary, and when model, so what you need to do is not only find the boundary, but also you have to come up with a description of how likely is it that a particular sample belongs into a particular class, okay? And discriminative is basically just focus on the decision boundary. You just give it the boundary and say, this is my, and this is it. But in generative case, you actually give it a probability distribution to define two different classes, okay? So here we have different generative classifiers. Okay, so to summarize, you have two paradigms. You know, we have rule-based systems where you have an input, you have hand-designed program, which is essentially your inverse problem, and you get an output. In classic machine learning, you have input, you have some hand-designed features, and from those features, you give it a, it will come up with an output. Okay. Representation learning is where you have input, you have features, mapping from features to output. So the features are also derived by the algorithm. On the other hand, a classic machine learning algorithm, we were putting in their hand-designed features. And deep learning is the newest idea, which of course we'll spend quite a bit of time talking about, is we use cascaded networks to identify certain features. And we add even more layers for more abstract features. And from using those features, we then predict an output. And this has actually revolutionized the image processing industry. Okay, a little bit of math towards the end of the class. So we have an input X and the output Y. So, and then we use something called a loss function, which measures the difference between the actual output and the predicted output. Okay. And what we do is we minimize this loss. And that basically tells us whether the machine has run the pattern. Okay. And to minimize that, we use something called optimization. Okay. And I will talk about that. So optimization basically means if y is a function of x, what is the x for which y is minimum? Okay. We could also solve it in a stochastic way using probabilistic approach to estimation. Okay, to summarize, machine learning broadly can be classified into supervised and unsupervised learning. And under supervised, you can have classification and regression. Unsupervised is mostly clustering, and then under clustering, you have different methods like k-means, hierarchical, Gaussian mixture, and so on. And classification also has different supervised method, and regression has a lot of different machine learning algorithms. So we'll go through most of these methods, and hopefully you'll have time to experiment with your own data on the application of these algorithms. So that's where I'd like to stop and maybe take some questions or comments. Okay, any question, comment?
So that optimization part that you were talking about.
Yes.
Sorry, sir. That is related it to deep learning part, or means I have seen it in deep learning, means that optimization and loss function concept. Is it there in machine learning algorithms also there?
Yes, I think almost every algorithm uses some kind of optimization. You will see that.
Okay,
so for example, the clustering problem we were talking about, right? So
yes,
you
sir.
want to measure the distance between, let me see if I can get a whiteboard here. I don't know how I can get whiteboard here. Anyway, so let's say that you're trying to, no, I can actually draw it. Yeah, just hold on. Okay, so let's say that I have this. Can you see my screen now?
Yes, sir.
So I have some points here, and then I have some points there, right?
Yes, sir.
So your algorithm wants to basically come up with two classes, okay?
Yes, sir.
So here, the goal would be to find these clusters such that distance of all of these points within the clusters is smaller than than any point in the other cluster, okay?
Yes, sure.
And also intra-cluster distance should be maximum, okay?
Yes.
So this is an optimization problem, okay?
Okay, sir. Yes, got it, sir. Thank you, sir.
Yeah, these things will be clearer to you as we, give more and more lectures. Okay, so next week we will actually do a little bit of hands-on practice with a very basic algorithm, and then go from there. All right. Any other questions?
So can
Yeah,
you
go ahead.
re-explain the semi-supervised learning? Like how is it different from unsupervised learning?
Okay. Yeah. So semi-supervised basically means that there is an intermediate steps. Okay. So here. So I have input, right? Then I have, say, neural network, okay? And then I have output, right? So given an input set to the neural network gives you an output. Now in the supervised case, you have the known answer, right?
Yes, sir.
So in the unsupervised case, you don't have the known answer. So in the semi-supervised case, you say that you know part of the answer, okay? How do you actually form it? There are many different ways. One approach would be to actually, let's say that you have a lot of known answers. So you can just try some part of the answer, known answer as training, and then use these for prediction. Okay, that is sometimes called a semi-supervised. But the other approach would be that I can take the output. Let's say that I have seismic data, okay? And I want to know the velocity, right? That's one application. So the input model goes through the input data goes to the neural network and it predicts velocity, but you don't know if this velocity is correct and you don't have any level data. So what we can do is we can say that, okay, the velocity and input may be related to each other using some equation of physics, right?
Yes, sir.
So then I can put that equation, and that then gives me predicted seismic data, right? So
Yes.
now your loss function is a comparison between prediction and, okay? Does
Thank
that
you, sir.
make sense? Yeah,
Yes, sir. Yes, sir. Thank you, sir.
welcome.